Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 12. We are in lecture 4. This is part 3, and we are talking about the maximum likelihood estimators, and we're right in the middle of an example, so we'll pick up there. Now let's look at the continuous case. Okay, the same problem. So xi is still binomial 1p, I 1 to n. Sigma is now in the set where sigma is now the set of p such that p is between 0 and 1 inclusive. Now we need to look at some cases here. Case 1. Now remember that for xi is equal to 0 or 1. So 0 if it's not a success, 1 if success. Okay, so technically xi could be 0 for all of these. So for however many n trials we have, we could end up with xi equals 0 for all of them. That means that the sum of xi would be equal to 0. Let's look at the case where sum of xi is equal to 0. So this implies that L of p, remember L of p is p to the sum of xi. So this would be p to the 0, 1 minus p to the n minus 0 equals simply 1, let's zoom back in, 1 minus p to the n. Okay? And the only thing that what maximizes this, remember that this is a number. The bigger the number in the parenthesis raised to the power, the bigger L is. So the bigger the number is, and remember p is between 0 and 1, the bigger 1 minus p is, the bigger L of p is. Well, if you set p to any value but 0, then this is less than 1. But if you set p equal to 0, then 1 minus 0 is 1. 1 to the n is 1. That's the largest value this can take. I hope you can see that. If not, work out a few examples. So this implies p hat equals 0. Okay. Now, case 2. Let's look at, so every one of the xi's could be 1. It could be a success every single time. These are extreme cases, but we need to look at them. X sub I, sum of x sub I equals n. Then we have L sub p is going to be p to the sum of xi, which is n. 1 minus p to the n minus sum of xi is equal to n. That's 0. This is 1. So this is p to the n. And if you take a number that's smaller than 1 and you raise it to a power, it gets smaller. 0.5 squared is 0.25. All right, so 0.50 goes to square it, it's 0.25. That's smaller. 0.9 squared is 0.81. So any number you take and you square it, if it's between 0 and 1, it gets smaller or closer to 0. Same is true if it's negative, but p can't be negative here. So this implies that p hat is equal to 1. This is the MLE in this case. Okay? So for this case, p hat equals 1 maximizes this. So let's take case 3. This is the case that most people concentrate on, but you can't forget these other cases. So this is a case where the sum of xi is between n, 0, and n, not equal to. Okay? So this tells you, so now, what happens when p is 0? Then L of 0 is equal to 0. Why is that? Because p is 0, so L of p equals p to the sum of xi times 1 minus p to the n minus sum of xi. Keep that in mind. If I plug in p is 0, then I have a 0 for this term, and I have a 1 for this term, because 1 minus 0 is 1 raised to any power is still 1. And so this means that L is going to be 0. This is never a max. Why? Because this is a product of, in this case, PMFs. And PMFs, the minimum they can be is 0. And so they can never be negative. They're non-negative values for PMFs. We've multiplied them, so L of P equals 0 is not a max for the likelihood function. Now, this also implies that L of 1 is equal to 0. Why? Because if I take 1 minus 1, I get 0 again. And then 1 raised to any power is 1. So 1 times 0 is 0. So again, not a max. All right? So this implies P hat, let's do this, is somewhere between 0 and 1. Okay? In this case. Okay. So let P be in the set of P such that P is between 0 and 1. And this implies L of P is greater than 0. Okay? Right? Because if this term, if P is not 0 and it's not, if P is not 0, then this term has to be positive. And here, if P is not 1, this term has to be positive because P is less than 1. Okay? So that implies that this is positive. Okay. So now, let's take L prime of P, where this is equal to d dP of L of P. P is our variable here. It's a function of P. Do not take the derivative with respect to X. That will mess you up big time. You will get garbage. So you don't want that. All right. So we have up here, oh, no, not there. We have here L of P. So I'm going to take the first term, and I have to take the derivative with respect to P. So that means the exponent is X. That's a constant with respect to P. So I'm going to treat this just like I do any exponent. So I'm going to take the exponent down to the front, multiply by P to that exponent minus 1. And then I take the chain rule for P, and that's going to be a 1. And then I take the second term and just put it there. We're using the product rule because there's two terms that have P in there. So for we take the derivative. So let's see. So we have the dx of x. Let's see, f of x, g of x. Trying to think about how I write this. F of x, g of x is equal to f prime x of g plus f of x, g prime of x. So that's the product rule, which we're using here. So we have the derivative of the first times the second. So we've taken the derivative of the first here times the second, 1 minus p to the n minus sum of xi, plus the first, p sum of xi, times the derivative of the second, which is 1 minus p to the raised to this power n minus xi. So I'm going to take the exponent down, and then I have 1 minus p to the n minus sum of xi minus 1, and then I need the chain rule on the 1 minus p. The derivative of 1 minus p with respect to p is 0 minus 1, so minus 1. You do not want to miss this negative sign. You will miss most of the points on the problem by doing so, because you will not get the right answer. You will make life difficult for yourself. So please, by all means, remember your chain rule. Okay, the derivative of what's in there. So now I can simplify, and this is equal to sum of xi, p sum of xi minus 1, 1 minus p, n minus sum of xi, minus, because I have this minus sign over here, so I pull this out to the front. So minus, and I'm going to put the constant here, or it's constant with respect to p. I'm going to pull that out to the front, just like we would. That's a number, n minus sum of xi. And then I'll have p to the sum of xi, and 1 minus p to the n minus sum of xi minus 1. And we're going to set this equal to 0. Don't fall into the trap of adding this to both sides. that can end up canceling out some of the possibilities, and again, that is not good algebra or good calculus actually. So or algebra. So don't do that. We're going to factor. Factor, factor, factor. I'm going to factor out the term p first, and I'm going to take the biggest exponent that's in both of them. This only has sum of xi. This has sum of xi. That's going to be bigger because x is equal to 0 or 1. Has to be the same or bigger than this one. So the smallest one is the sum of xi minus 1. That's what I'm going to factor from both. Okay? So I'm going to factor this. So I'm going to end up with p sum of xi minus 1. And then while I'm at the factoring, I'm going to take the smallest of these two exponents. Okay? And it's going to be this one, because there's a minus 1 there. So I'm going to end up with 1 minus p to the n minus sum of xi minus 1. Now I need to know what's left. So I have this sum of xi left. I've taken this whole term out, so it's just a 1, so I don't need to write a 1. And then I've taken everything but one of these 1 minus p's out, because I factored out n minus sum of xi minus 1, so there's a 1 minus p left. And then I have a minus sign, please don't forget that. And then I have my constant, n minus sum of xi. And then I've taken all but one of these p's out, because I took out sum of xi minus 1 as a factor, so there's a p left. And then I took all of these out, so that's just a 1. And this is equal to 0. Now, up here we said that p hat has to, for this case, has to be between 0 and 1. It can't be 0, it can't be 1. Well, if it can't be 0, then I can divide by this term here. And if it can't be 1, I can divide by this term here. So why am I able to do this? Because here, if I want to leave this, I can say that for this to be equal to 0, if this term is equal to 0, p is equal to 0. And I've already said it's not. So p sum of xi minus 1 equals 0 implies p equals 0. And we know that that doesn't maximize this. That minimizes it. So we don't want that. And then, because up here we said that p is 0, L is 0. We also said if p is 1, L is 0. So then we have, so this is 1, this is 2, and this is 3. So 1 is here. 2, 1 minus p to the n minus sum of xi minus 1 equals 0 implies the only way that can happen is if this is 0, and that implies p equals 1. But L of 1 equals 0, so that's not a maximum either. So that leaves us with, therefore, the MLE is found by solving 3 equals 0. So I have sum of xi times 1 minus p minus n minus sum of xi quantity times p is equal to 0. I need to expand this so that I need to separate out the p. I need to have all the terms of p together, and then I can solve for p. So again, you do not want to do any divisions here, or you're going to get you may get a wrong answer. You will get a lot of points taken off. So please don't do that. So we're going to expand and do our algebra properly. Sum of xi minus p times sum of xi. I just expanded this first term. And then I've got, I'm going to leave the minus sign here because that way I won't get it wrong accidentally. So within the parenthesis, I'm going to say p times n is np, and then minus p sum of xi. Now I'm going to get rid of the brackets by distributing my negative sign. So I've got sum of xi minus p sum of xi minus np plus p sum of xi. This is really important, equals 0, because this and this cancel. And I'm left with the sum of xi minus np equals 0. And if I solve this, I can add NP. Now I only have P in one term. So this implies that NP is equal to the sum of xi. And this implies that P is equal to sum of xi divided by n. This is x bar. So we need to check if P, oops, getting ahead of myself, if P equals x bar is a max. Now, you might be tempted to use the second derivative test. In this case, it's a mess. So you don't want to use the second derivative test. Okay? So I'm going to remind you that I'm going to use first derivative test. And I'm going to go to a clean sheet of paper so I have plenty of room. So here I have L prime of P is equal to, let's see, it was sum of xi minus np. Let's make sure that that is correct. Oops, wrong one. Here we go. We had, where is L prime of P? So L prime of P, so remember that since we don't need this term, since we don't need this term and we don't need this term, neither one of those are zero, okay? Neither one of those can be zero because we said that P equals 0 and P equals 1 are not in the solution for this. So we can divide both sides by these and get rid of them because 0 is over here. So we're left with what's in here, which is going to simplify to sum of xi minus np. Okay? And this is an important thing to do, or else your math is a monster and you don't want to do it. Okay? So it's important to note that you can divide by this because these are constants and they are not equal to 0. And since they're not equal to 0, you can get rid of them as far as your... these don't minimize or maximize. Or you can say I'm going to ignore them and it's based on this term. That's a more proper way of thinking about it. So remember that when we did this, which we said was number 3, we ended up with, where is it? Here. Sum of xi minus np. So I'm going to take the derivative, or I'm going to use this, and I'm going to rewrite it in terms of x bar. So I need sum of xi divided by n, that's x bar, but to get this, I have to multiply. So what I'm going to do is, to do that, I'm going to go n over n, sum of xi. And this portion here is x bar. So I'm going to be left with n times x bar, and then I've got np. So I've got nx bar minus np. This is the easiest way to do it. So I've got nx bar minus p. Now, the first derivative test says p is here, x bar is here. I'm going to look at, we know that, I'm going to say L prime of p is here. We know that it's 0 at x bar. So, 1, what sign is L prime of p if p is less than x bar? 2, what sign is L prime of p if p is greater than x bar? So here I've got n times x bar minus p. If p is less than x bar, then this is going to be positive because p is not as big as x bar, and therefore x bar minus p is positive. So that means over here, I'm positive for the derivative. Now, if p is greater than x bar, then I take x bar minus p, and p is bigger than x bar, then this becomes negative. So it's going to be negative here. So L is going to be increasing here, and then it's going to be decreasing here. And so that means that at x bar we have a maximum. By the first derivative test. And you have to show this work every time. You can choose second derivative or first derivative. If at this point it's almost inevitable that it's better for you to choose the first derivative test than it is the second derivative test. Okay? Now, if we hadn't simplified this, we would have had p to the, p to the sum of xi minus 1, 1 minus p to the n minus sum of xi minus 1, and then we would have had and then we could have had nx bar minus np, and we could have factored out the n, so we could have said np sum of xi minus 1, 1 minus p, n minus sum of xi minus 1. And we would have to make this, we need to make the exponents in terms of x bar. So this would end up being nx bar minus 1, 1 minus p to the n minus nx bar minus 1, and then we would have had x bar minus p here. And so we would have to plug in p everywhere. Well, this is not going to change signs here if I make p less than x bar. And this is not going to change signs if I make p less than x bar. Okay? This is the only thing that's going to change signs. But you have to really think about these to know that they're not going to affect it. So again, I hope I've shown you a easy way to do this and to get the MLE in this situation. Okay? So next time we'll talk about using the log likelihood function, and that's a lot easier. So please update your formula sheet with what you've learned so that you can you know what the likelihood function is, and make some notes on there so that you remember that it's in terms of the parameter theta. In our example it was p, but the parameter general thing is theta. If you have questions, come to virtual office hours. If you need help more urgently than that, then by all means email me and I'll get back to you as soon as I can. Please take care of yourself, and we'll see you next time.